Hi, in this video, we're going to take a look at achieving convergence when doing a Bayesian exploratory factor analysis model. All right, so a viewer had a question about having trouble with getting their Bayes FM BE uh, Bayesian exploratory factor model to converge. Okay, and so this video is to help them out. Number one, number one thing you want to think about with this, if you're having trouble getting a model to converge, and this is true with any model that is fitted in an iterative process, including like generalized linear models, but this most often comes up during Bayesian. If you're having trouble getting convergence, you probably have a poor data model combination. All right, so one thing that we're going to strongly want to consider is change our prior. If we can't get it to converge, you probably have either a bad prior or a bad model structure, maybe both. And making adjustments is probably the best way to go. All right, so I'm going to go through, I'm going to take the code from 2.3 Bayesian factor analysis from modern psychometrics with R. I've got another video covering the code here. But here we're just only focused on getting things to converge. What can I do? All right, so if you're having trouble getting a Bayesian exploratory factor model to converge, you probably have a poor data model combination. That just means that more than likely what you believe to be true about the situation doesn't match what the data is saying. This algorithm is going to be like a heat-seeking missile. It is going to work as hard as it can to get the best fit that it can. But if it's getting conflicting signals, it's not going to be able to land on one. If the data and the model agree with each other, it's going to converge much, much faster. Okay, so that's something to think about. If it takes a lot of iterations to converge, consider changing up your model structure. And that's true for any model building that we do that has a convergence effect. So make sure that your model jives with your data. So if you have no idea which prior to use, you can increase the variance to a crazy amount to make it an uninformative prior. And by doing that, we're setting it up so that the data is able to speak more clearly and the prior's influence has less impact on what's going on. Also, another thing that needs to be considered is my data ready for modeling? All right, so I want to make sure that my data doesn't have problems with it before I actually do the modeling. Because if there's problems, it's gonna create a problem down the road, right? All right, so make sure that if I have any data errors, that they're resolved. I might not know which ones are erroneous. I might be able to spot it by looking through good, clean, accurate data. Make sure that missing values are resolved, outliers are resolved. Also, I want to make sure that my data looks approximately normal if that's reasonable for my project. All right, so if I'm in a situation where it would be permissible to go and do a Boxcock-Johansson log or square root transform on a column of data to make it have a distribution closer to the normal distribution, I should do that if I can do that for my project. Now, you're gonna have to work with your stakeholders, for what is appropriate. That's a really good way to go. Now, when it comes to data errors, missing values, and outliers, now we might be omitting values. Also, I might want to impute and fill something in. So let's say that I see a value. I know that that one entry is absolutely wrong. I could, get rid of the entire row of data, or maybe I could just treat that entry as a missing value, impute, give a reasonable guess, either with, univariate imputation, put in the mean or median for the entire column, or maybe do something like a misranger, fill in with using a model. And I could do that for the errors, the missing values, and outliers, where so missing values, I'm filling in the blank, and then errors and outliers I could be replacing. For me personally, when I'm dealing with outliers, I like to replace extreme values with the 95th quantile or the 5% quantile. That way, the extreme values get pulled in a little bit so they don't pull the rest of the model towards them. I find that that works very well. All right, so now here are some other things that we can try to get our Bayesian factor analysis model to converge. First and foremost, rescale my manifest variables to have mean 0 and standard deviation 1. This will be especially important for the standard deviation 1. That's going to be the more important aspect of these two. It'll also make it easier to interpret what's going on in a little bit. Also, we could go through and use classic correlation analysis, factor analysis, and principal components to determine the number of factors, the number of manifest variables that we need to have within each factor. All right, so what I'm going to do is, I'm going to do an exploratory model, and I'm going to figure out what looks right in a non-Bayesian model. And then what I'm going to do, I'm going to tinker with the Bayesian model fitting to match what I see in my exploratory model. Now, if you're paying attention to Bayesian statistics, you know that this is very much not Bayesian. We're supposed to come up with our prior before we look at our data. I believe that when we see informative prior, when people do Bayesian statistics, I suspect that more Bayesian statisticians and data scientists actually use this than they're willing to admit. So basically, this is cheating. From a Bayesian point of view, this is cheating. But if I need to, feed my family, get the job done, move on to the next project, I'm going to do this. You know, Ultimately, my goal is to make my stakeholders happy and to get paid and move on to the next project. All right, so I'm going to use correlation analysis, factor analysis, and principal component analysis to decide how many factors I should have. And in my Bayesian factor analysis, I'm going to set it up so that it's prone to give me that number of factors. All right, so here in Bayes FM, K max is the maximum number of factors that I can have. Okay, so I'm going to set K max equal to that value that I get from the exploratory model. All right, so what will end up happening is that all the values 1 to K max minus 1 are going to be basically wasted iterations in the fitting process. But this is the best that we can do with this software. Now, NID is the minimum number of meaningful manifest variables for each factor. And so I'm saying each factor has to have at least this many variables going into it. And I'll judge that by using the frequentist approach exploratory model. All right, so then I can also do simulations with the prior distribution to figure out the parameters that's going to force the Bayesian model to look like my classic factor analysis model. All right, so there's two ways to do this. We're going to look at like the correlation matrix aspect using with the prior simulations, and we can look at the number of factors prior, and we're going to find values that match for this very well. All right, so I'm going to set kappa to strongly favor the number of factors in the exploratory model that I found here. I'm going to set nu naught and s naught to favor the eigenvalue results that we want. So with this one, we're going to choose nu naught and s naught so that we don't have our prior clumped up at 0 for the minimum eigenvalue, and we don't have 1 for the maximum correlation is how we're going to proceed. Also, there's different structures of the prior. There's Wang Ward and inverse Wishart. The default is Wang Ward, and just looking through, I feel like this one is like by now, at this point, the standard way to go. But if one isn't working, I can always bounce to the other. So whichever one I'm on, I'll bounce to the other if I'm having trouble getting things to converge. Also, we can increase the number of iterations. All right, so my advisor, when I was in school, told me to double the number of iterations. If things look the same with when you double the iterations, that leads you to, a strong conclusion. So if you double the iterations and things look good, you didn't need to double the iterations, assuming they look the same. And also, if I double the iterations and the problem isn't fixed, it's probably not an iteration issue. Now, we could brute force it by just kicking up to a crazy number of iterations, but honestly, you don't want to do that. You don't want to be sitting by your computer waiting. Also, something that we could do, we could increase the burn-in. So in the burn-in, the Monte Carlo Markov chain kind of needs to get like warmed up. And so here we're saying, hey, go through a bunch of iterations to get close to the distribution that we actually want. The first ones we're just going to completely throw away, not even consider them. So we could kick this up so that the Monte Carlo Markov chain has time to reach the distribution that we want. Then it starts actually saving the iterations that we're going to use. Now, really, if we want to avoid the Monte Carlo Markov chain fighting on convergence. We want to set it up so that the mathematics of the model and the data just match together overall. If default settings of the Monte Carlo Markov chain don't work out for us, we're basically like really fighting the situation. We're making it harder on ourselves. So this should be kind of like a late stage, try. I want to try the other things first and then go to increasing the number of iterations, increasing burn-in. We can also set the number of steps between kept iterations. We can also like adjust that also, but that's more of a Monte Carlo Markov chain conversation, so I'm not going to dwell on it here. We can also adjust the beta prior shape parameters for the no loading probability. And so here, once again, increase the variance of what's going on to try and set it up so that our data can speak without having the prior, fight what the data is saying. All right, so now let's go ahead and actually take a look. So here I'm going to set up my workspace. I don't want a lot of digits printed out, and I want to avoid scientific notation. I always use Magrittr and ggplot for like every project, so I put these on here for everything. Now I'm going to work through the example that is in 2.3 of modern psychometrics with R. And so we've got the privacy data set. And I'm going to rescale, and I'm using the same same notation as in the textbook. I'm going to rescale things. So this is going to set it up so that I'm going to have mean 0 and standard deviation 1 for each column. Between the two, the standard deviation 1 is going to be more important, and it'll also make it easier to interpret the coefficients as we go through. If I don't do this, what could end up happening is that like the high variance columns can have undue influence on what's going on, and the low variance columns will have less influence, even if they really shouldn't have. So imagine that we're talking about like the time that it takes to run a race and in seconds, and we have 100-meter dash, we have 400-meter, 200-meter, 800-meter, and we have all the way up to marathon, and everything's in seconds. And I want to do factor analysis on people's run times. Okay, what's going to end up happening is that the marathon, because it's so much bigger, so much variance, it's going to have more influence than the rest of the columns put together if I don't rescale. And so rescaling is very important for this. Now, if everything is about the same variance, about the same magnitude of numbers, rescaling is not so important. I do it every single time though. Okay, so now let's do that classic analysis to get an idea of what is a reasonable model to end up having. And so remember that this is the Bayesian cheating approach, that I'm going to identify a prior that agrees with my data, then I'm going to fit my Bayesian model. In literature, we'll call this an informative prior. Okay, so let's do a correlation plot. And I'm going to make this easier for my eyes as a human being, I'm going to use hierarchical clustering to organize the columns in the correlation plot. So I'm going to use hierarchical clustering with Ward's D linkage, and I feel like there's three groups here. And so I put down three. All right, let me give you a little, all right, there we go. So here, when I look at this, you can see that the hierarchical clustering identified three groups for me. Now, it would have been reasonable to also say there's two. You see how all of the APC columns form another square? And so two different possibilities. It's up to your eyes. What do you see? What do you think is right? I feel like three is the right answer, but if you and I were working on a project and you said two and you're like very firm about it, I would just be like, all right, two, dude, whatever. Okay, so here it looks like to me, I have the DPCs are forming one group. The lower number APCs are forming a group. The higher number APCs are forming a different group. And so, all right, this can help inform my prior. All right, so I look at this, I've got three different factors is what I'm leaning towards at this point. And then I notice that each one has three or four manifest variables going into them. So this square represents a factor, represents a factor, represents a factor in my tentative analysis. And I can see that there's four variables going into this one, three going into this one, three going into this one. All right, so now I've got something to work with. So Kmax is equal to 3, NID is equal to 3, because NID is the minimum. Now, I could also do a regular frequentist factor analysis, and principal component analysis like corresponds to that. So let's go ahead and take a look at that. Okay, so print comp. So there's two base R ways to do principal component analysis, PRIN comp and then PR comp. Two different ways to go. Use whichever one you feel more comfortable with. When I look through here, so I'm looking at the proportion of variance, and notice that there's not much of a change between these two. There's not much of a change between these two, not much of a change between these two, not much of a change between these two, and so on. So that leads me to believe that there are at most four factors, okay, in this method of fitting a factor analysis model. Now, you could convince me that you see one factor, two, three, or four. It's a subjective analysis. When I look at the scree plot, which is equivalent to this, if I was to put a line going from the top of each bar, I'm looking for where there's an elbow, okay? And so here I kind of see something, and then it kind of flattens out. You can see that there might be an angle here. So that's leading me to maybe think that possibly four. Okay, now this is fitting in a different manner than other factor analysis methods. Other methods of factor analysis, you'll lead to other conclusions. Be adaptive. Just take it all in and figure it all out. Okay, so here I'm fitting with PR comp this time, so I'm still in base R. And I can go through and the proportion of variance, once again, I see the same values. This supports that there's at most four. Everything is practically speaking, up to like minor round off errors and sign switching, everything's the same. But let's look at the loadings. Okay, so when I look here, and this is going to be different than my final conclusion down the road, by the way. I see the largest values in PC1 corresponding to the APCs. So I've got 0.4, 0.3 going on with the APCs, and they're all negative. And then the DPCs are lesser in magnitude, and they're all positive. Okay, so if this was a factor, I would see that the APCs are leading with approximately equal value in a negative manner, and then the DPCs are contributing in a positive manner to a lesser extent. Okay. And so what I want to do as I now analyze this, I want to find a cutoff and use that as say, hey, everything below a certain threshold is a zero. As I look through, all right. So now it'll get tougher and tougher as you get later down the road. Here, the first one is like a contrast between the APCs and the DPCs. All right, this is pretty small. Let's ignore that. All right, start with the big ones. It's generally what you want to do. All right, so I see, 0.4, 0.5, 0.5, 0.4. All right, so I feel like PC2 is the DPCs. All right, now let's move to PC3. All right, I'm going to ignore the smaller values, and I've got 6, 5, 4, and then 1 and 2, maybe 3 could be included, but these are all pointed in opposite directions. So I see a contrast between, so I'm going to disregard the smaller values for DPC. So I'm going to just, pretend that these are 0. And in my analysis of this, I see a contrast between the lower number APCs and the greater number APCs because of the opposite sign. All right. So now let's keep it going. And so I'm going to ignore the smaller values here. All right, so this is there. And now it's getting harder to figure out what's going on. All right, so I've got APC4, DPC2, DPC3, and then the largest value among them. And all right, so now I don't really have an intuition onto this because of subject matter knowledge. If you look at the documentation of the data set, the APCs are one class for the variable, and the DPCs are more similar to each other. And so I'm feeling like there's something going on with the grouping of the APCs and the DPCs that I saw in the correlation analysis. All right, so now I've got something to work with. So let's keep on moving. And this plot is equivalent to what we saw before. I could go in and do another form of factor analysis until I really feel confident about the results. At this point, I feel okay to proceed. All right, now I'm going to set the maximum number of factors and the minimum number of manifest variables per factor to reduce unwanted model fitting. All right, so Bayes FM is going to go through and fit a whole range of possible models when it does the Bayesian model computations. And frankly, if I want 3 as the number of factors and I want 3 as the minimum number of variables going into a factor, then you know what? I want to stop at 3. Now, it's going to consider other values, but I only have so much control of the situation. So I'm going to leave it as is. Okay, so now let's go ahead and simulate priors so that I can pick values of the parameters on the priors that will lead to the model that I believe is correct from my cheating Bayesian analysis. Okay, so I'm going to go through a range of possible values. The default value in this function is going to be kmax plus 1. All right. Whenever you're working with a function and you don't know what parameter values to try, my personal trick for a grid search is I take the default value, I cut it in half, and then I double it. So that gives me three different values to just try and explore. And if it's a serious project, I'll use the results there to try other values and continue my grid search. So the default value is Kmax plus 1. So then I'm going to take Kmax plus a half, Kmax plus 2, and I'm going to have three different new zero values. Now, when it comes to SO, now this is our scale parameter. The scale parameter, the default value in the function is 1. So I'm going to try a half, 1, and 2 as an easy grid search. I don't have much experience with this function. I'm not real sure what I should do. So I'm just, making a guess and running with it. Okay, so this is going to go through all the combinations that I have. So there's going to be 9 different models that are going to be tried. And then let's go ahead and take a look at the summary. All right, so first, let's look at the eigenvalue because that's more important to me personally, that I don't want 0 eigenvalues. Okay, and so to avoid a 0 eigenvalue, I personally want the 5% to be away from 0. Okay, so when I do that, I notice that, hey, here we go. All right, and then here we go. All right, that's a little bit bigger, and here we go. All right, so I look through here, and I notice that new equals 5, S naught equals 0.5 gives me, a decent value. And then new naught equals 5, S naught equals 1. And then new naught equals 5, S naught equals 2. All right, so that leads me to conclude that new naught equal to 5 is a good choice. Now, the S naught, I don't really know yet. Okay, so now let's look at the maximum correlation. All right, so with maximum correlation, if I had perfect correlation between factors, then I have redundant factors. And there's no point in having that level of redundancy. So what I want to have the 95% away from 1 if I can. All right, well, here it's a little bit harder to see. But as I look through, all right, so I mean, this really isn't that great of results. I would like to see more of a buffer here, but it's about as far away from 1 as the minimum eigenvalue was from 0. And I go through here, and once again, the same ones are giving me that the shift away from the value I don't want. And so with the minimum eigenvalue, I'm looking at the 5 percentile quantile. With the correlation, I'm looking at the maximum or the 95% quantile. Now we can visualize this. Okay, so you can see that practically speaking, I have 3 different models going on for this measurement of it. All right, so for this aspect, now there's going to be other eigenvalues involved, just that with this simple situation, with this data set, this model, it ended up that I really have just 3 results. And now, remember, I don't want an eigenvalue close to 0, and I don't want correlation close to 1. So the parameter values that are overlapping with this yellow curve and overlapping with this teal curve, I don't want those. I don't want them because of both sides of it. So now the purple looks attractive to me. I look at the purple, well, that's new equals 5 with the variations of S naught. All right, so I conclude that the new naught should be 5. I'm unsure about the scale parameter, which is going to be, think of that as like the dispersion, possibly the variance, depending on the situation of the model. And so I don't want to bias the situation. So I'm going to go ahead and just crank it up. I'm going to set that equal to 2. I could keep iterating this. I could keep doing grid search until I was really, really comfortable with the results. I'm not getting paid to do this video, so I just did this and I'm rolling with it. Okay, so now I've figured out the correlation matrix prior parameters. So this step is done. Now let's take a look at the kappa for the number of factors. Okay, so we're going to go through. So at this point, I've decided that I want at least three variables connected to a factor. I want to have exactly three as my output of number of factors. And so now I want to set up so that the kappa parameter, the concentration parameter for the factors prior leads to the result that I want. And so once again, I'm going to do a grid search and I see, so I don't know what to try. So I'm going to do 0.1, 1, 10, and 100. Okay. And I tried I tried a couple of different things. I looked at, help documentation examples, and I looked at the example from the textbook. This is not the values from the textbook. Um, so when we look at this gives me the results. What really tells me the story is right here. If kappa is 0.1, we can see that it's going to be prone to having one factor. Well, that's not what I want. When kappa is 1, then it's going to be prone to 2. When kappa is 10, it's going to be prone to 3. Okay, that's the result I want. And then if kappa is 100, because I kicked it up, I can see that it's going to be prone to 3. Okay, so I want, of these values, I want kappa to be 100. I really wasn't satisfied with the plot when I did 0.1, 1, and 10, so I just tried 100, and that's what I landed on. All right, so you can see that there's a pretty big difference. I'm basically guaranteed to get 2 or 3 off of this kappa. All right, so I'm going to set kappa to 100, which is rather large. Uh, this will be a bias model, but it's a bias model towards towards the results I believe are correct anyway. All right, so I'm going to go through and I'm going to use the data. I've already set this to 3 as the minimum number of variables, of manifest variables connected to factors. I want to have at most k, or at most k max, which is going to be 3. So it will consider 1 factor, 2 factors, and 3 factors, but it's not going to waste time iterating on 4, 5, 6, so on factors. I've established the nu naught. I've established kappa, and let's go ahead and keep it going. I didn't set S naught. Huh, okay. I forgot to do that. But I've got the results, so let's keep it going. Now, it takes a little bit of time to do a Monte Carlo Markov chain. One thing you can do is set your iterations and your burn into lower numbers for like your exploratory aspect. You want to do it fast, you want to do it quick, you want to figure something out, and then as you're tuning and adjusting things, then when you feel like you have the right parameters, the right values, that's when you kick it up a notch. All right. So now something that we can do is that we can set it up so that after it's done with the fitting, the results as is off of BEFA. BEFA might not have the factors in the order that we want, and the sign values might be opposite of what we want them to be. So what we can do, we can reshuffle the factor order to make it so that the first factor is like the most variance accounting for. And we can also multiply by a negative sign without changing the mathematical value of the model, and that'll set it up so that we can have some easier interpretation of things. So on this step, I'm shuffling the factor order to make sure that the first one is the one that I feel like that has the most oomph in the analysis. And then I'm doing post sign switching to make sure that the negative signs are easier for me to interpret if I'm going to go through and start digging in. All right, so let's look at our actual model. All right, so it just gives me the printout of what I gave it. It said, I know that the columns are ordered the way I want them. I have the signs set up the way I want them. Multiplying by a negative sign on a factor is not going to alter the mathematical value of it. It's just going to make it point in the opposite direction. So it's just easier this way. All right, so now let's look at the summary. It gives me the information. Ended up having three factors. I did a pretty good job of forcing that in. Now, this is an easier example to work on. There's really no issues with getting convergence to happen on this particular case. Also, I'm setting it up to do it the smart way. So that's part of the reason why. So it's an easy data set. I'm setting it up to work out quickly. Boom, I got it. All right. And so now, we can look at the factor loadings. And here's the average with the standard deviation, idiosyncratic variances of each of these. And here is the factor correlation matrix, the correlation between 1 and 2. Remember that we have entire probability distributions going on. And so with the probability distributions, we don't have like hard firm values. We have like an average and a standard deviation on the correlations. And so, the interpretation is different, but this is part of the power of Bayesian statistics. And so like here, we can look through each of these. You'll notice that these are not correlation zero like they would be if I would have done principal component analysis, but that's okay. They don't have to be perfectly uncorrelated. Now here we can look at the Metropolis Hastings sampling process. And so here you can see that every time that there's a tick at the bottom, the iteration was accepted. So I set it up so that things are going to go easy peasy lemon squeezy. All the iterations were accepted, and it's very confident that because of how I set it up, very confident that the number of factors should be 3. This line is not bouncing around at all. Here's the posterior probability of 3 factors. It's saying 100% because I forced it to. Now the posterior means is 1 every single time. And you'll notice that we have things set up the way that I thought it was from the correlation analysis, that the lower number APCs connect to a factor, the larger number APCs connect to a different factors, and the DPCs connect to a third factor. And now here we can actually look at the loading values. And so the darker red means that there's a stronger connection between the two. And then we can look at the correlation between factors. So we see a correlation between the larger and the lower APC column factors. Okay, so I might look at this, I might go, 0.46 is too large for my project. I don't want this much correlation in my factors. Maybe I would want to change now to 2. It's up to you. It's going to be a subjective judgment call. Do what you think is best. All right, so the main takeaway, number one thing that you want to consider if you're having problems getting your Bayesian factor analysis model to converge is that you might have problems with your data model combination. You can adjust your prior to basically agree with your data. This is cheating in Bayesian statistics. I think this is way more common than people will admit. If you see the words informative prior, then you can be like, they probably took a look at the data, picked a prior that matched, and then went with it. Now, that doesn't mean the model is wrong. It just means that it goes against the philosophy of Bayesian statistics. Now, it is Bayesian, and we have more power in our analysis when we have a Bayesian approach compared to a frequentist approach. We have a more complete representation of the system. And with that, it might be I had a frequentist model that I agree with, but with the frequentist model, I don't have all the oomph and the tools that Bayesian statistics gives me for a more complete analysis. Well, I can go ahead and, use this approach to get a deeper, more complete analysis going on with this. Other thing to consider, data prep. If I have errors, omissions, outliers in my data, I need to resolve those. So missing values, fill in a reasonable value, either by univariate, like median or mean mode values, or I could go in and use a model to go in and fill in missing values. Also, I can treat like errors. If I can identify an error, I can go, hey, I can treat that as replace that with a missing value and then do imputation on that. And also, if I have outliers, extreme values, I could trim it down. If it's extreme to the right, I could trim it down to the 95th quantile on the data set on that column. And if it's extreme to the left, I can replace it with a 5% quantile for that column. And that will help prevent outliers from over influencing my model. Another thing that I want to consider, make the column look more normal. All right, so I could try square root transform, Box-Cox transform, log transform, Yo-Johnson. These are all options. And I strongly recommend that you rescale your data to have a mean 0 and standard deviation 1 before you start doing this whole process. All right, I hope this video has helped you. Uh, Life is short. Do math.